in terms of limits. The limit of the relative change in value of the function, f of x minus f of a over x minus a, the other point x approaches. We've seen an alternative viewpoint from the definition, the establishment of a linear approximation of associated error term for the values of a function near close to the base point. And the derivative appears there as the linear term in the non-constant linear term in the linear approximation. We've seen the main basic important properties of the derivative: the linearity, product rule, chain rule, the quotient, and some treatment of some of our simple polynomial type functions to derive their derivatives from first principles. So what we have coming up in the remainder of this chapter is focusing on some application areas of this. Mainly, I think the main important application to consider is the one of optimization, finding maximums and minimums of certain quantities, solving optimization type problems. But before we get on to that, we've got a few more, I don't know if they're properties of differentiation, but a few more techniques, extra add-ons, extra little bits of tools and so on that we use when considering the derivative. The first one is about inverse functions. So we considered functions and their inverses in the functions chapter whatever it was, 3. And we pointed out a nice graphical relationship between the graphs of a function and the graphs of its inverse. So here we have two functions, f and g, and we're assuming that f and g are inverses of each other. When you compose f and g, f after g, g after f, you get the identity function that sends every argument to itself. And we described in chapter 3 how their graphs are actually straight reflections of each other through this reflection line through the y equals x reflection. That kind of makes nice sense because when you're inverting a process, you're interchanging the start and the finish. You're interchanging the x and the y, so to speak, and that interchanging is geometrically the reflection. Now that has implications for the derivatives of these two functions. So like a basic type question that should be occurring to us is, how do the derivatives of a function relate to the derivatives of its inverse? Are they wildly different? Are they completely unconnected? Well, be surprised if that was the case. So we're expecting a strong relationship between them. Remember, the derivative is the gradient, the slope of the tangent line. So here's our original function f. Here's a certain base point x0. And here's the tangent line to the graph at that point. Now the tangent line, naturally we think about it as a ratio of side lengths of the right angle triangle. So the ratio of the y difference of this triangle divided by the x difference. And what happens to that what happens to the whole picture when you reflect it? Well, when you reflect it, the reflected line is going to be the tangent line of the inverse function. And the triangle reflects to a right angle triangle with the tangent line as its hypotenuse side as well. But what happens to the y and x? Well, what was the length of the side parallel to the y-axis? When you reflect it, of course, it goes to this over here, which is now the length of the side parallel to the x-axis. And vice versa. What was parallel to the x-axis is now parallel to the y-axis after you performed the geometric reflection. So what was the ratio, this y quantity divided by this x quantity, giving you the gradient of the tangent line? And that quotient is flipped. So we take the reciprocal of that quotient, 1 over that quotient. You interchange the numerator and the denominator positions to get the gradient of the tangent line to the inverse. So that idea is summarized here in this relationship, that the derivative of x with respect to y, that would be the derivative of the inverse function, the function that gives x as a function of y. So that would be the slope of the gradient to the function g depicted. Whereas this dy dx, that we kind of think of as the derivative of the original function f. Okay? And there is this reciprocal relationship. So let's look at a concrete function and see an application of that, what we're talking about. just to kind of confirm its validity in a relatively simple case. So we'll consider a function. We'll consider the function f from, well, we'll take it from the positive reals to the positive reals. So r plus is all those real numbers that are positive. I'm restricting the domain so that the function definitely will be invertible. So let's consider this function to be the one defined by, so f of x is x cubed. Okay, so it's the cube function. It takes an argument and it cubes it. Now its derivative, and the derivative of f prime of x, well, we've already treated the basic polynomial type functions. Its derivative will be 3x squared. And its inverse function, is g of y. Well, what's the invert in the inverse transformation to the cubing transformation? Well, it's to take the cubed root. Yeah, y to the power 1/3 cubed root. So when we differentiate this, then g prime of y, the derivative of y, will be 1/3 y, and then we subtract 1 from the power, so that's going to be subtracting 3/3, so that's going to go to minus 2/3. So let's check the reciprocal relationship. So we must recognize and appreciate what points we're evaluating these derivatives at. Okay. So let's check the special relationship at the point, the base point A. But now what's the corresponding y value to that? The corresponding y value to that is, of course, a cubed. I mean, it's the cubic function here, something like this. Here's a, here's the point a cubed. That's what the function f does. Then it's a cubed. So what we're going to do here is, when we evaluate f at a, the derivative of f at a, we get, of course, 3a squared. Okay, so that's the gradient of the tangent line to the function f at the point a. It's gradient 3a squared, whatever that quantity is. But the derivative of g, well, you see, we want to evaluate it at the corresponding point. So we evaluate the derivative of g at the point a cubed. We have our formula here. It's 1/3 times y, so the y here is a cubed to the power minus 2/3. Okay, that doesn't quite look exactly like it's the reciprocal of that yet, of course, but there's some work to do here with the indices. We're taking a power of a power. Remember, when you take a power of a power, exponent of a power, you multiply the two exponents. That's the basic rule of manipulating exponents. So this becomes 3 multiplied by minus 2/3. So in other words, it becomes a 3rd a, and these 3's cancel, so it's the 3rd a, the minus 2. Which is, now we recognize, so this is the confirmation, confirming here now that this is exactly 1 over quantity 3a squared, i.e. 1 over f prime. So that's an example of illustrating, for a particular function and its inverse, verifying that this reciprocal relationship does indeed hold between the derivatives. The derivative of the original function evaluated at A and the derivative of its inverse function, which is a graph somewhat like this. That might be entirely accurate. But... Oh, yeah. Yeah, but it shows you how what we justify speaking in abstract terms, or just a general function and its inverse. They're thinking of the graphs, the way the graphs are reflections of one another, and how that relates to, how it transpires in a particular example. Where we're doing direct computation of the derivatives and observing this exact reciprocal relationship. Okay. So that knowledge of that relationship can sometimes help us when we're working with functions in the the next kind of technique or tool that sometimes arises can be called parametric differentiation. It's basically an application of the ideas of the chain rule. And so we have the idea that the derivative has a geometric meaning. It's the slope of the tangent line, gradient to the tangent line, to the graph of a function. Yeah. But there's all sorts of curves, there's all sorts of interesting curves and sets in the plane which are defined not by straight functions of the form y equals f of x, such as this curve, this parabola type curve. Now that is not, if we take it as x is the horizontal axis and y is the vertical axis, that curve is not the graph of any function y equals f of x, because at any point x, the curve is got 2 points at any particular x value, an upper point and a lower point. And functions, by our concept of functions, our definition of what a function is, a function has to be single value. You give it an argument x, it has to just give you a single value. So that can't be the graph in the form y equals f of x of any function. But if one way we can specify that curve is to give a pair of functions. Okay? So 2 separate functions, one for the x coordinate, one for the y coordinates of the points. We often use t for the variable when we're speaking parametrically, and we can think of t as a time-like variable. So at any particular time or any particular value of t, these coordinates give you a point on the curve. And running time, forwards or backwards, will sweep that point through the curve. You see, at t equals 0, we're at the point 0 minus 1. So that will put us at this point here where the curve kisses the y-axis. And as you run time forward, you get positive x coordinates. As you run time forward, you get increasing y coordinates. So that will send the point up on the upper branches. But if you start from 0 and run time or run the parameter in the negative direction, the x coordinate still gets bigger, but the 2t minus 1, that will get even smaller than minus 1. So that sweeps the point out along this. Now, okay, what are we talking about what's the differentiation point we want? The concept of a tangent line to points on this curve still holds true. You can still pick out any point on the curve, and you can conceive of the tangent line to the curve at that point. A line whose rate of increase is exactly the same as the functions at that point. So the question is, how can we arrive at a nice expression for that slope of the tangent line out of the 2 parametric functions? Okay? So we can conceive of it this way. So what we seek is this quantity dy dx. Even though we don't explicitly have a function, a complete function y equals f of x that will produce all of that graph. But that's the kind of quantity we're seeking, the change in y over the change in x, which will give us the gradient of the tangent. But we can get at it by first thinking of an application of the chain rule. So we seek the derivative of the quantity y with respect to the time t. By applying the chain rule, we can express that, we can think of y as a function of x. So first differentiate it with respect to x, and then differentiate the x function with respect to its variable t. So that is thinking of the function y of t as really a composition. Function, or some function applied to the value x of t. So we get that relationship there from the chain rule. Now we've just talked about inverse functions and so on. So what we want to isolate here is the first term here on the right-hand side, the dy dx term, the slope part tangent line. So we need to divide both sides by dx dt. So we have dy dx now is dy dt, the derivative of the y function, divided by dx dt, the derivative of the x function. Or if you like, you can present that using the concept of inverse functions. That derivative there will be equal to the derivative dt dx, where you're talking about the inverse function to the x coordinate. And by again applying the chain rule, you can also obtain second order derivatives of y with respect to x as well. That will correspond, that will be relative to the curve as well. So let's see an example. Let's see an example of this. Which one are we going to do? Yeah, take the second curve here. So this figure in 4.8. We'll have a look at this one. This is example 4.7 in the notes. So we're thinking of the, I'll switch on the overhead now in a second. So we're thinking of the parametric curve. Parametric curve with these coordinates here, cosine t times the cosine 2t. And similarly on sine of t minus the sine of 2t. Okay, so if we were to put that into a MATLAB or a similar mathematical package and ask for a parametric plot of that curve, we would see that nice pleasing curve in 4.8. Okay. And for any given value of t, you can observe the point on the curve given by that value of t. As t changes, your point will move smoothly around the curve. So what we would like to get a nice expression in terms of t giving us the slopes of the tangent line. The slopes of tangent lines to this curve at a value t, slope of which tangent line? Well, the slope of the tangent line to the point on the curve given by a particular value of t. So we can use this parametric differentiation technique. So the quantity dy dx, which is this desired gradient, dy dt divided by dx dt, as we've outlined. And so then, making use of our nice table, our formula handbook, our table of derivatives, if you like, we can obtain this. So the first, the quantity dy dt, so we look at the y coordinate, we want to differentiate this. We can apply linearity, it's a linear combination of functions, difference. So its derivative will be the difference of the derivatives. So we're applying linearity. T will be cosine of t. We're going to subtract, we're applying linearity times the derivative of sine of 2t. For that, we should use the chain rule, because that is a composition of the function sine after the function which is multiplication by 2. Let's find t by 2. So the sine part will differentiate to a cosine with the same argument. Then applying the chain rule, we have to further then multiply this by the derivative of the inner function. The derivative of the inner function there is 2. 2 times t is 2. That's the quantity dy dt. And then we simply divide that by the corresponding derivative of the x function, which will be minus the sine of t minus 2 times the sine of 2t. This time applying exactly the same considerations to the x coordinate function. This time the functions are cosine. You still need an application of linearity and the chain rule there as well. But just say notice the applications of linearity and the chain. So this is our formula. And for any given value of t, will provide us with the slope of the tangent line, the gradient of the tangent line to the parametric curve at that particular value of t. Now we do have a rational type expression here, an expression with a significant quantity in the denominator, and that can cause problems because what if that quantity reaches 0 in the denominator? But we can reconcile that behavior to what's going on in the graph, because sometimes you see, various points at the graph, you can imagine what the tangent line looks like. As you travel along the graph and approach this crossing point of the x-axis here, you see that as you get close there, the tangent lines are getting extremely steep in the negative sense. Okay. Until when you actually cross the axis there, you've got an exactly vertical tangent line. And so as you approach that crossing point, the gradients of the tangent lines will be getting larger and larger in negative absolute value until they informally reach the value of infinity at the crossing point. So that will correspond to zeros of that expression in the denominator. Okay. Because that, just in your notes, that plus is a tie. No, that plus is correct. When I wrote it on my notes, I put a second minus sign there, but it's minus cosine, so it'll put plus. Yeah. So that's correct. The version I wrote down. So the possible zeros of this denominator expression will correspond exactly to either this point out here, so it'll be the value of t that gives you this crossing point out here on the axis, which is a vertical tangent, or this one in here, which also has a vertical axis, vertical tangent. Okay. So 2 more tools we want to look at. Again, just different ways of using the derivative. So again, and this, I think they're both, it's really just making the chain rule do some work for us in certain circumstances. So we have the notion of implicit differentiation. So normally, typically, as we originally set it up, we're faced with a function y equals f of x. And we want a derivative of y with respect to x. So we differentiate the function. However, it isn't always the case that relationships between the variable y and x are presented in such a nice, clean way, where we have the quantity y expressed as a given function of x. Sometimes the relationship is presented in a different way. So that original way, y equals f of x, we would refer to that as an explicit definition of y in terms of x. Okay? An explicit definition. The relationship is given by the function f. And if the function f is presented to you as a standard function or some combination of standard functions, you'll be able to take its derivative. But relationships can be presented implicitly as well. So we might instead have some kind of equation or condition on the two variables, such as these, the sum of squares must be 1, or the difference of the squares must be 1, or the sign of the product must be 1. These are three examples of implicit functional relationships between the quantities y and x. Okay? If y and x must satisfy one of these conditions, then if you change y, if you change x a little bit, the y will have to change in response to keep the condition true. One of these we should recognize as the equation of the unit circle, the first one. So you're familiar that if you had a point on the unit circle, i.e. a point with x and y coordinates satisfying that first condition, if you change the x coordinate of the point a bit, you better change the y coordinate in response in order to stay on the circle, in order to keep the condition true. So there is a functional relationship between y and x implicitly there. If that condition is to be true, we're at a point that satisfies the condition, and we want to vary the x coordinate, the y coordinate has to change in response to hold the condition true. So there is a functional relationship. If we change x, we get a corresponding change in y. But the function, what the precise function is, isn't declared implicit in the condition. So how can we proceed from here? Well, we can still obtain, provided the conditions are presented in terms of basic functions that we know about, we can still obtain a nice, a useful representation for the derivative, for the gradients, tangent lines, to the curves represented by these conditions. So again, it's an application of the chain rule. So what we do is we accept that there is a functional relationship between y and x. Okay, so there will be a derivative dy dx that we can find. And the procedure we take is to differentiate the whole condition. Okay, to apply the derivative to both sides of the condition. So typically one side might be a constant or something relatively simple in terms of x, say. So you can take its derivative. And anywhere you see the function y, you treat it as a function of x and operate the chain rule accordingly. Okay. So here's a worked example here. So we're going to take this implicit definition here. X squared plus 2y squared minus xy plus 2x equals 0. Okay. So that defines a relationship between the y and x variable. Y and x must, for whatever values they have at a certain instant, they must satisfy that equation. So what is going to be the rate of change of the y variable with respect to changes in the x variable? Okay? If you wobble the value of x, the value of y will have to wobble in sympathy with it to keep the condition true. So we differentiate both sides with respect to x. On the right-hand side, we've got the constant 4, so its derivative with respect to x is 0. Simple enough. On the left-hand side, we're differentiating this big expression. At the top level, this big expression is a sum of 4 quantities. It's a linear combination of 4 quantities. So we can apply the linearity. We definitely want to appreciate everywhere where these basic properties of differentiation are being used. So first of all, we're applying linearity. We can work out the derivative of the big expression by differentiating each of the 4 parts and adding or subtracting them together according to the original linear combination. But we're differentiating with respect to x, remember. So the derivative of x squared is 2x, fine. What's the derivative of 2y squared? Well, what we recognize there in the quantity 2y squared is a composition. It's a composition between, first the function y is applied to x, and then the function that doubles a square is applied to y. Y is squared, and then the resulting value is doubled, multiplied by 2. So that's a composition of functions. First the function y is applied to x, and then the function 2 times the square of the argument. So we can apply the chain rule to differentiate that compound function. So we differentiate the outside first, which will be 2 times 2y. And then we multiply by the derivative of the inner function, the function that was applied first, which is the y. Now, how do we represent that? Well, we simply represent it as dy dx, the derivative of y with respect to x. We don't know the explicit functional relationship between y and x, so we're not going to put down some formula in terms of x there for dy dx. We're simply going to represent this notion that we're trying to investigate, dy dx. So that's an application of the chain rule to that term. Again, for the third term, x times y, we want to apply the chain rule as well. Okay? That's a product of, sorry, not the chain rule, the product rule. What we recognize in that product x times y is two functions of x multiplied together. One function is the identity function of x that just gives you x. And the other one is this mysterious, for the moment, function y. Function we don't have an explicit definition. So we need to apply the product rule. So we hold the first factor the same, multiply by the derivative of the second, which is dy dx. Then we hold the second factor the same, y, and multiply by the derivative of the first factor, which is x. Sorry, which is 1. Derivative of the function x with respect to x is just 1. Has a negative sign in front, so we get negative signs in front of both parts. Let's find the product rule for that third term. Fourth term, there's no y involvement, just a straightforward function of x, 2 times x, which has the derivative of 2. So what we obtain here is now a new expression on the left-hand side, which is a combination of x's, y's, and the derivatives dy dx. Now we're interested in investigating, remember, the derivative, the slope of the tangents to curve defined by that original issue. So we simply just do some algebraic manipulation then to make dy dx the subject of the formula. For any terms that don't have a dy dx, send them over to the other side, reverse their sign, and factorize out the dy dx and divide both sides by that factor, and that isolates the dy dx's. Of course, we recognize it doesn't, again, things are again implicit. It doesn't give us an explicit function of x as the derivative. It still needs to rely on the associated value y. So in order to actually evaluate this, in order to actually make use of this, to actually evaluate numerically a particular gradient of a particular tangent line, we would need to know both the x and the corresponding y value of a point on the curve. But it still gives us a useful representation of what the derivative is, not only applying to the kind of bottom level independent variable x, but also to the associated variable y. So that's the technique of implicit differentiation. Taking an implicit definition of a functional relationship between two variables and obtaining relatively useful expressions for the derivatives by operating appropriately the chain rule, the product rule, and the linearity rule for differentiation. Final technique we're going to look at is that of logarithmic differentiation. So logarithmic differentiation will apply in situations where if we're differentiating with respect to a variable x, say, and we meet x appearing in the exponent position. Okay? Nothing we've said so far really addresses directly the point of what do you do when the variable you're differentiating with appears in the exponent position. We've seen examples of polynomial terms where the x is in the base, and we have numerical exponents. But what if x itself is in the exponent position? Well, there's various approaches. You can either remember a particular formulas for what the derivative is, and that's okay. But the more and more formulas we have to remember, the harder it is, and the more and more risk we run of misremembering formulas as well. Common source mistakes where we recall things incorrectly. So it's generally a good idea to rely on some core set of principles that we can be very confident of, and remember the techniques for deriving further principles from. That's important. It helps us accurately reconstruct things and remember things, but it will also help us discovering new things as well. So the basic idea, and I don't remember by heart any formulas for doing this kind of differentiation, I just remember that there's a trick in the technique. The technique is to change the relationship, transform the relationship by using the logarithm function. The logarithm function I regard as a more fundamental thing, and I remember properties of the logarithm. So we take this relationship y equals x to the power of x and take the logarithm of both sides. By default, we'll use the natural logarithm. But basic property of the logarithm is that the logarithm of an exponent is the product of the exponent with the logarithm of the base. Okay? You might remember it as kind of the logarithm of a to the power b is b times the logarithm of a. So the exponent quantity comes out of the logarithm and multiplies the logarithm of base. So that's good. Then, so the function of that is to take the x quantity out of the exponent position. And we then use implicit differentiation technique. So we differentiate both sides with respect to x. So we've got the derivative of the logarithm of y and the derivative of this product. On the left-hand side, we operate the chain rule. The derivative, because this is a composition of two functions, the logarithm after the function y. So we differentiate the logarithm, which gives us 1 over y, multiplied by the derivative of y, which we represent as the derivative of y. Differentiating the right-hand side, we see a product of two functions of x times the logarithm. So we have to operate the product rule. Keep that the same, multiply by the derivative of the logarithm, which is 1 over x, plus keep the logarithm the same, multiplied by the derivative of x, which is 1. So we get 1 over y dy dx is 1 plus the logarithm of x. We want to isolate dy dx, so send the y back over. You multiply both sides by y. Then we know what y is in terms of x. We do have y explicitly in terms of x. Standard functions, it's x to the power. So we get this final resulting formula for the derivative of y with respect to x, when y is x to the power of x. So what I would encourage you to take away from that is, in any situation where the variable you're differentiating with respect to, wherever that appears in the exponent position, a useful technique for working with the process of differentiation there is to first transform it by using the logarithm. Using the basic properties of logarithms, how logarithms of exponents behave, using the knowledge of what the derivative of the logarithm is, you can fairly quickly get a relatively nice expression for the derivative of the original function. Okay, so that's the example we're ending with of that. For the tutorials this week, so you may still be working on the extra tutorial sheets I handed out. I don't have another one yet. I'm going to give you another big one on some of the applications. But there are further questions in the end of chapter exercises that you'll find useful to work with. I think anything really now up to question 8 would be in play. So there's a bunch of questions there. You can take those along with any of the other tutorial sheet questions that you haven't done yet. Satisfaction. So that will be some of the work we can do in the tutorials this week. And Saeed's got his lecture now, and he's taking the lecture tomorrow. So when I see you next week, we'll begin the sections on the applications of the derivative. Okay. Chief interest is going to be the optimization one. We're also going to look at a few other topics. Taylor series again. We'll give a justification for L'Hopital's rule. And we might look at some basic kinematics applications. Okay, so folks, thanks for your attention. So it's just 10 to now, so we can